Welcome back to another episode of Online Calculus 2. I'm your host, Professor Anderson. Let's go ahead and pick up with the next part, our introduction to sequences. All right, now we introduced in our intro in the last video, introducing what an infinite series is. Now the key to understanding infinite series, how we're going to add up an infinite amount of numbers, is introducing something simpler called a sequence. And that's what we're going to get to in this online lecture. Now, if we ask the question, what is a sequence? There's a pretty simple answer, just an ordered list of numbers. We're going to call those numbers A, and then with a different subscript on it, the subscript is going to indicate the order in that list. Now, this by itself is pretty boring, and I'll even admit that myself as a math professor and mathematician. A sequence by itself, this sounds really boring and completely unmotivating. But this will be the key to understanding infinite series and some of those peculiar results that we got to in the introduction. 1 plus 2 plus 3 plus 4 plus 5, why that might come out to equal negative 1/12. Now, before we go on to defining what sequences are with a little bit more proper mathematical notation, let's just give some examples of these. The first one there is the sequence of natural numbers, 1, 2, 3, 4, 5, and so on. The second sequence, the reciprocals of the natural numbers, 1 plus 1 over 2 plus 1 over 3, so on and so on. And then the third one, probably the most famous sequence of all, the sequence of Fibonacci numbers, where we start with the two numbers, 1 and 1, and then add those to get the next term in the sequence. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, so on and so on. Now, one of the main questions we're going to have to answer with sequences to get to infinite series and understanding them is what happens to the terms of a sequence as we go deeper in that list. So as we start writing out and looking at more terms further into that list of numbers, what happens to them? And what this is introducing is the concept of a limit. We're going to call the subscript, the index, n, and we're going to ask what happens to the terms as n approaches infinity. And this is where we'll introduce the concept from calculus, your Calc 1 course, that of a limit. All right, let's get to the two ways that we're going to kind of encounter to define sequences. The first way is kind of like a function. We're going to call this an nth term formula for a sub n. And basically what this is a formula for a sub n in terms of n. We're going to call n the index. For this type of function, we're going to think of the index as being the input. So if we plug in some sort of a positive whole number, 1, 2, 3, 4, or 5, so on and so on, this nth term formula spits out the nth term in that sequence. Let's take a look at some examples for this nth term definition. Let's say we had the formula here for a sub n defined as 1 over n. Notice the starting index starts with n equals 1. And if we just plug in 1 and then increase the index values 1 at a time, we get this sequence of numbers. The first term with n equals 1 is 1. Then we adjust and increment n to 2. Plug that in, we get a half. Increment n to n equals 3, we get a third. And then 1/4, 1/5, and so on and so on. Now, one of the benefits of the nth term formula approach, rather than the next type that we're going to get to for defining sequences called a recursive definition, is that you can plug in the index and get any term in that sequence, no matter where it is. So for example, here, if we wanted the 100th term in this sequence, we just plug in n as 100, And to that formula, 1 over n, we get the 100th term, a sub 100, as 1 divided by 100. All right, here's one that's a little more complicated, but still the sequence is defined by an nth term formula. Now it's -1 to the n plus 1. Think of what happens with powers of -1. If the power is even, you'll get +1. If the power is odd, you'll get -1. So pause the video, give yourself a little bit of time to try to write out a few terms for this sequence. Welcome back. If we start by plugging in n equals 1, the numerator, that -1 to the n plus 1, will become +1. And then in the denominator, when n is 1, we get 2 times 1 plus 1, which is 3. So our first term for n equals 1 should be a third. The next one, where n is 2, notice now you get -1 to the third power, which is going to be -1. And in your denominator, you'll have 2 times 2 plus 1, which is 5. And you can probably see the pattern here. Notice the expression 2n plus 1 is an odd number when n is an integer. And then the numerator, -1 to the n plus 1, that's alternating the sign back and forth. So for the third term, we should get +1/7, then -1/9, then +1/11. If you were to continue, you should find the sixth term in the sequence is -1 over 13. All right, a related question, kind of the opposite, is if we're given a sequence of numbers, can we construct or find a formula for the nth term? This is a little bit harder. There's not a lot of kind of like definitive ways to do this in mathematics, but pause the video, give this one a try, see if you can find a simple formula for a sub n that gives you all these values, those terms in the sequence. All right, how are we going to do this? How are we going to find a formula for the nth term? A key way to do that is to try to recognize patterns. Now, if you look at the numbers there, 2/3, 4/9, 8/27, those are all powers of 2/3. So we might think our formula here might be, let's say, 2/3 to the nth power. In order for that to be consistent, we have to start the index with the value 0. That way we get the first term as 1. Anything to the 0 power is 1. Now this is one way to construct that formula, a sub n as 2/3 to the nth power. In order for that to be consistent, our starting index has to be 0. There's going to be places later in the course where it might be preferable to start with the index with the value 1, in which case if we want to do that, the starting index is value 1, we have to use our formula here, 2/3 to the n minus 1th power. Now when you plug your starting index in, n is 1, in that exponent you get 1 minus 1, which is 0. 2/3 to the 0 is still 1. So there's kind of 2 equivalent ways to find that formula. Now these were all examples of the first way to define a sequence with an nth term formula. A second way that's going to be not encountered too often in our course, but it's something I want to prepare you for mathematically for what might come next, is called defining a sequence recursively. And this builds off an idea from computer science and programming called recursion, which is basically a process of repeating something in a self-similar pattern. All right, let's take a look at a simple recursively defined sequence. This one is going to be familiar from some of the examples we mentioned earlier in the video. Let's define as our recursion formula, a sub n equals a sub n minus 1 plus a sub n minus 2. And what that recursion formula says is each term in the sequence is the sum of the previous two terms. If you think of how you would count, if you consider a number n, the numbers that came before that, the first two, would be n minus 1 and then n minus 2, which are the two numbers preceding n. Now, in order for some programs and algorithms to work in computer science, you have to start with what are called seed values that kind of start the algorithm. Here, we're going to take as our starting values for A1 and A2. We'll define them both to be the values 1. Now, if we use these values in our recursion formula, our now goal is to get what A sub 3 is. We can plug in n as 3 everywhere in that recursion formula. Notice all the n's are in the subscripts doing the labeling, the index. Plug in n as 3, we get to here. A3 is A2 plus A1. And now we can plug in our values that we were given. A1 and A2 are both 1. So we should find here A sub 3 is the value 2. All right, we can go to the next term where n is 4 to get A sub 4. This is now the sum of the previous two values, A sub 3 plus A sub 2. Right above, we just calculated what A sub 3 is, and we already were given what A sub 2 is. So we should find here A sub 4 comes out to be 2 plus 1, 3. And you can probably see the pattern here. We're just going to add the previous two values. This sounds like the Fibonacci sequence. We should find here A5 comes out to 3 plus 2, which is 5. And sure enough, this is defining recursively the Fibonacci sequence. Now, let's take a look at a different recursively defined sequence here. Pause the video and see if you can write out the first few terms for this second recursively defined sequence. Welcome back. The first value that we're given there is A sub 1. Our goal is now to maybe to get the next one, A sub 2. If I plug 2 into the recursion formula, we get this expression, A2 is 1 plus 1 over A1. And if you plug in your values there, you should find A sub 2 comes out to be 2. We can now get the third term in the sequence, A sub 3. This is defined as 1 plus 1 over A sub 2, 1 plus a half. And if you add those together, you should get 3 halves. Moving on to n equals 4 for A sub 4, the fourth term in the sequence. We have 1 plus 1 over A sub 3. A sub 3 is the value 3 halves. Keep in mind, when you divide by a fraction, you can multiply by the reciprocal. So 1 divided by 3 halves, that comes out to be equivalent to 2/3. If you add 1 and 2/3, you should get 5/3. And if we go through one more term, you should find A sub 5, the fifth term in the sequence, comes out to be 8/5. And if we write all the terms together, we get our sequence here defined recursively: 1, 2, 3 halves, 5/3, and 8/5, and so on. All right, now that we've seen a few examples, we can get to kind of the main question. What happens as n goes towards infinity? What happens to the terms as we go deeper in that list? And this is introducing the idea of what we'll define as the limit of a sequence. Now, we're not going to spend too much time on this, since in your Calc 1 course, you kind of got a thorough introduction to limits of all sorts. Here, we're going to be making use of a lot of ideas earlier, which were limits at infinity. When x approaches infinity, now we're just using kind of a different variable, n. All right, so we're going to consider the case here. a sub n gets closer to some number L as n approaches infinity. And this will be a way that we kind of understand the definition for the limit of a sequence. If the terms a sub n get closer to a number L, we say that expression has the limit as n approaches infinity of that number L. Now think back to your Calc 1 course. There were some limits that did not exist. So keep in mind, for limits to exist, the quantity or function has to approach a single finite value. If the quantity approaches 2 values, the limit doesn't exist. And if the limit approaches infinity, it also technically does not exist. All right, now I want to quickly get to some very useful results that you kind of maybe already know about from your Calc 1 course on limits. And a way to do that is a useful way to think of sequences as a special type of function where we don't plug in any number, but we plug in only positive integers. So let's say we were to define a sub n as some function, some formula, but instead of plugging in a real number x, we plug in a positive integer n. Now, how we relate this example, what we'll call a continuous function, a function that you might have been familiar with through your previous courses. How we get a sequence from this is just looking at the values that are positive integers. So 1, 2, 3, 4, 5, and so on. Now, since real numbers are also some of those numbers, 1, 2, 3, 4, and 5, we kind of get some of these sequence values overlapping, sitting on top of the continuous function. So the f of x values gives you this continuous graph. Plugging in only positive integers, we get this discrete graph or discrete function. And notice it's pretty much the same thing, just with gaps. We're not plugging in every x value, just n values, 1, 2, 3, 4, and 5, and so on. All right, but notice here, while the function has a limit as you let x approach infinity, because the sequence values sit on top of that continuous function, the sequence also approaches the same limit. And what we get is this nice, useful result that if we have a function that has a limit L as x approaches infinity, then the sequence defined by that function approaches L as well, but now as n approaches infinity. All right, let's take a look at another quick pair of examples. Let's say we had the function 1 over x. As x approaches infinity, 1 over x approaches 0. Notice that fits the form 1 over a big number. Since x is approaching infinity, 1 over a big number gets smaller towards 0. The same thing happens for 1 over n. It's pretty much the same graph, but just with discrete values there rather than a continuous graph. So for here, the sequence defined by 1 over n, as n approaches infinity, that also approaches the limit value 0. All right, before we get to some examples on evaluating limits of sequences, let's take a look at a few quick results that are useful. This is kind of a collection of things from your Calc 1 course. Primary tool for dealing with limits with indeterminate forms, 0 over 0 or infinity over infinity, is L'Hopital's rule. Here, the function or sequence has to be defined as a fraction, and if it is with an indeterminate form, you can evaluate the limit by differentiating numerator and denominator. All right, another useful result is when we have a sequence defined as some number raised to the nth power. And we're going to call that base number some real number r. So our term here is r to the n. All right, let's take a look at a few possibilities. Maybe we have the value for r less than 1. Let's say r is 1/2. if you were to take increasingly larger powers of a half. Think of what happens if you hit with your calculator, 1/2 times itself, and then just keep hitting equals. The number keeps getting smaller and smaller and smaller. Powers of a half, 1/2, 1/4, 1/8, 1/16, get smaller towards 0. All right, another possibility is if r equals 1, but this is pretty boring. 1 to any power is just 1. So there's really not much to say about the case where the value for r equals 1. If the value for r is bigger than 1, this kind of has the inverse result of the first part. Instead of the numbers getting smaller towards 0, if r is bigger than 1, powers of that keep getting bigger towards infinity. And then a kind of a fourth case for consistency is, what if r equals -1? Write out the terms for the sequence -1 to the n, and you'll find you only get 2 different numbers in that sequence, +1 and -1. Now the terms are finite numbers there, 1 and -1, but half the numbers are 1, the other half are -1. So this sequence won't get closer to a single number, which is why this limit, as n goes to infinity, of -1 to the n does not exist. That sequence approaches 2 different values, +1 and -1. All right, we can summarize all those possibilities here in this with these 3 results that are going to be useful. The 3 possibilities are if the absolute value of r, allowing for negative values, if that's less than 1, the limit comes out to 0. If r equals +1, the limit is just 1. And if the absolute value of r is bigger than 1, the limit here for r to the n comes out to be infinity. All right. Let's take a look at another useful result. This is on the squeeze theorem. So earlier you would have encountered this maybe towards the beginning of your Calc 1 course. It basically says if you have a function f of n squeezed between 2 other things, and those 2 functions approach the same limit, then the thing in the middle also approaches the same limit, L. This doesn't pop up in a ton of places for our course, but it pops up enough that I wanted to make you aware of it and recall that. A fourth useful result is kind of a nice theorem for when you have a sequence or a simple sequence inside of some sort of function. If that function f that the simple sequence is inside is continuous, and most basic functions that we'll encounter will be continuous, what this says is the limit of that sequence inside the function, we're allowed to basically bring that limit inside the function and look at first the limit of the sequence, which we stated was L in this theorem. And then basically we just plug the limit value inside that function, bringing the limit inside, and we get here that the limit for the sequence for f of a sub n approaches f of L. All right, and then a last one, again, just to deal with some tricky examples, is there is a limit definition of E that I want you to be familiar with. You might have first encountered this in your pre-calculus course when you were being introduced to compound interest and continuous compounding. This was what appeared in the PERT formula for continuously compounded interest. And we have this, the expression 1 plus 1 over n raised to the nth power. That approaches E as n approaches infinity. All right, let's close this lecture with a few examples. So here you'll be given a sequence. The nth term formula, a sub n, and asked to evaluate the limit of those as n goes to infinity. So we have 4 of them here. Pause the video, give them a try, and we'll check back in a few minutes. All right, welcome back. Parts A and B go rather quick. We're going to apply L'Hopital's rule. Notice for part A, the numerator and denominator both approach infinity. They both get bigger as n approaches infinity. So we have an indeterminate form, which means we can apply L'Hopital's rule, and differentiating now with respect to n as the variable rather than x, we get as our derivative for the numerator 3 and the derivative of the denominator 6. And that limit just then simplifies to 1/2. Part B also goes rather quick with L'Hopital's rule. Notice in the beginning, n squared approaches positive infinity as n gets bigger. E to the negative n, that approaches 0. So we have an indeterminate form here, but of the type infinity times 0. We need to convert that function to a fraction. E to the negative n can be put in your denominator, and you get n squared divided by e to the n, and then it's a matter of applying L'Hopital's rule twice. So apply L'Hopital's rule once to get 2n divided by e to the n, and then apply L'Hopital's rule again, since you still have an indeterminate form, infinity over infinity. Applying L'Hopital's rule that second time, 2n differentiates to 2, and e to the n differentiates again to itself. The final limit you have here, that expression or function, 2 divided by e to the n, that fits the form of 1 over an increasingly bigger number. Since your denominator is getting bigger, that fraction as a whole gets smaller towards 0. Moving on to part C. This one is actually simple, provided we recognize that we can rewrite 2 to the n divided by 3 to the n, all as a single power of 2/3. That just comes from using some basic exponent rules. And what we might notice there is 2/3 to the nth power. The r value that we referenced in some of our useful results is 2/3, which is less than 1, which then means 2/3 to the n as n approaches infinity. Since r is less than 1, that approaches 0. So we should find for our whole limit here that we get 1 for the limit of the whole sequence. All right, part D is probably the trickiest of all, simply because the squeeze theorem is probably a little bit unfamiliar. You probably haven't used it in a while. All right, and what we're going to point out first is that as n goes to infinity, cosine of n, that limit, doesn't exist. Think of the graph of cosine. It's an oscillating wave-like graph. It's just kind of oscillating back and forth, never settling down or approaching a single y value as you go very far to the right. Now, how we can get around this, even though cosine of n, that limit as n goes to infinity, doesn't exist, we can kind of take a look at squeezing cosine of n divided by n squared between two other functions. The starting place to construct this compound inequality that does the squeezing is to think back to basic properties of sines and cosines. The maximum and minimum values for sine and cosine are -1 and +1. So cosine of n is between -1 and 1. If we divide all three parts of that compound inequality by n squared, we get this one, where now the inside part, the middle, cosine of n divided by n squared, that is the term of our sequence for the limit in part D. If we notice the limits on the left and right, -1 over n squared and 1 over n squared, they both approach 0. The squeeze theorem then tells us that the thing in the middle, the limit for cosine of n divided by n squared, also has to approach 0. All right, that concludes this online lecture on sequences. Make sure to thoroughly review and understand this before moving on to the next part of the course, dealing with infinite series.